The speaker is Lorenzo Vorabbi, and he's an industrial PhD student at the University of Bologna. And his research focuses on new architectures and training methods to efficiently deploy binary neural networks on embedded systems with real-time constraints. And the topic, the title is Optimizing Data Flow in Binary Neural Networks. So take it away.
Yeah, thank you. Thank you, Thomas, for your kind introduction. It's an honor and pleasure to be here today, being part of this great community. And I'm going to show the results that I achieved with my PhD advisors that are Davide Maltoni from the University of Bologna, and Stefano Santi, a technical manager in Datalogic. So I basically cover the deployment of the neural networks on edge devices with real-time constraints. And when we talk about the efficiency of a neural network on the edge, we are talking about two main entities. One concerns the training algorithm, so all the methods or the algorithms that can be used to allow the model to be trained to get a better accuracy in terms of the binarization, model optimization itself, and then also the architecture. So what kind of architecture or connection of topologies can be used to improve the efficiency and accuracy as well. And these two entities are tightly coupled. My work primarily focuses the embedded CPUs equipped with a SIMD coprocessor, but this kind of opportunity can be easily deployed also to FPGAs and extended TPUs, who knows, maybe in the future binary TPUs. And of course, the binarization had the great benefit of reducing the silicon area on the chip. The goal of this work mainly addresses the efficiency of the model. We are more interested into reducing the inference time of the network, and we can also sacrifice sometimes some digits of accuracy of the model. And to this purpose, I'm going to show you a new training scheme we developed to inject the knowledge or to compress the data of the data flow in a binary neural model, because there were still some bottlenecks in there. And then the subsequent optimization of the best normalization layer, which is useful and necessary for binary neural networks to get better accuracy. And I'm going to show you also an implementation, like a high perspective implementation of our binary direct convolution for ARM Neon architectures. Now I want to show you a couple of use cases where binary neural network can efficiently improve the inference time of the network. I'm not going to talk about something that could be employed in the future. This is going to be part of the new generation of readers, checkout system, and already it will go in a production phase, actually. So in this case, in the slide you can see a typical image acquired by a reader in a TNL application. And this kind of application is a really intensive computation in terms of the amount of pixels analyzed. There are very huge images. And the goal is actually to decode barcodes, but the block that takes a lot of time is the localization of the two-dimensional barcodes. So the idea here is to detect the finder patterns of the barcode. Here, for instance, you can see in red L, the data matrix finder pattern, or the three red spots, you can see the QR finder patterns. And the binary neural network can effectively speed up this kind of application. Here I want to show you the new generation of the self-checkout models, where in this case the market is the retail market, where there is the produce recognition. So the customer usually has to pick up vegetables, fruits, and has to put on a weight scale. And usually, so far, what the customer has to do is to digit the number to get the ticket. And instead, here the goal is to have an autonomous system, an AI-driven method that can reduce the choice, the list of the choices to the customer, and this can be done with a binary neural network model. And in this case, there is the prediction of the vegetable type or the fruit, and also if there is or not a bag, and the kind of a bag. Here, just a brief recap of what is binarization. So instead of computing the expensive operation, or the multiply accumulate operation, we take basically the sign bit, both from weights and inputs, and we replace the operation with XNOR and pop count operation. Sorry. Of course, the advantage is to highly reduce the memory footprint, and also the inference time will impact it. This is how the binary neural networks were usually trained, because the problem with binarization is that it's not differentiable. So what is done usually in literature, in green, you can see the forward pass where the sign bit is extracted, and during the backward pass in red, the sign operation approximated as a linear function clipped in the interval -1 + 1, and then there is the implementation of the binary operation here, that is basically XNOR and pop count. Anyway, there are still some bottlenecks in binary neural networks, because actually after the XNOR and pop count, data is still at 32-bit floating point. Here in the top of the slide, you can see the case of a BGG model where there is the convolution, then the batch norm, and then convolution again. On the bottom side, you can see the residual blocks, and in red, it is highlighted the bottlenecks, in this case, floating point 32 bits. But for our target platforms, floating point and fixed point really doesn't matter. It really depends on the bit size. So here the question is, how can we move to 8-bit? If we take a look to the output ranges of each binary layer, we could argue to, okay, why don't we perform a post-training quantization naively, quantizing the output to 8-bit. In this part on the left side of the slide, you see the output ranges of the binary layer before the batch norm in green, while in red you see the outputs after batch norm. So the outputs are much more compressed, while on the left side, if we should apply naive 8-bit quantization, you're going to lose some data, not too much actually, but for residual blocks, the situation is more complicated, and a lot of information is gonna wasted. So the question, how can we effectively reduce the data width, increasing the data flow without affecting too much the accuracy? Here, for the VGG model, we can see in the block number as 1, the current solution of the binary neural networks. In red, we inserted a clipping operation during the training phase. This is actually different from the post-training quantization that could be done, because here we are injecting during the training phase the constraint of to compress the data inside the sweet range of 8-bit quantized values. And this actually has another benefit during the inference time, because the XNOR and pop count logic, I mean, using the SIMD coprocessor equipped on the Cortex-A platforms of ARM, the Neon, can be performed with saturation arithmetic, so directly accumulating data over 8 bits. And then there is the well-known conversion in literature that replaces actually for VGG model when you have the batch norm between 2 binary operators with a threshold operation in fixed point. The situation is pretty similar for residual blocks. Slightly changes because this clipping operation is inserted also after the binary, after the addition operator, in addition to the same place of the VGG block. And the difference here is that the best norm operator has to be quantized with 8 bits. And so here the novelty is that only 8 bits data type are flowing through the layers along the pipeline. Unfortunately, if you try to train from scratch a binary neural network model enabling the clipping operation, you're gonna get the same good accuracy as you expect. And sometimes also the network won't learn at all. And we found out that the clipping operation, at least at the beginning of the training, is completely prevent the topmost layer to be trained properly. So what we usually do, we perform a first training stage where the clipping operation is disabled. So this allows all the binary layers into the network to be properly trained. And after that, we perform a second fine-tuning training step where the clipping operation is enabled. Usually this second block, this second stage, requires few epochs to allow the model to recover the same accuracy previously reached. Here we have the formulas of the batch normalization optimization, that basically when batch norm is inserted in between two binary operators, it can be converted to this here, to this. Doesn't. Oh yeah, in the block colored in pink here, yeah. If it, yeah, here is converted to a threshold comparison, and so it basically doesn't take cost at the inference time. Here we have how we quantize the batch normalization operation. So actually, the input from the pop count and clipping logic is to 8 bits. Internally, to preserve the accuracy, the computation is done with 16 bits wide, but then at the end of this block, there is a scale of the output that convert the data type from 16 to 8-bit, and this is ready to go to the next block of the addition operator, always performed with saturation arithmetic. Here there is a lot of information in this slide. I just want to give you some key points of our implementation of the binary direct convolution. Here on the top left part of the slide, you see the input volume 3x3 by 128 channels. That each sample is 8-bit wide. This input volume is convolved with the same size of the kernel, and the input is flattened on local stack, extracting the sign. And also, in this case, depends how data is organized, and it is possible to achieve some slightly improvement depending on that. But here, in the top part of the slide, you can see the extraction of the sign bit and the XNOR operation producing in this row the output of XNOR. And then the goal is to implement the pop count operation on an ARMv8 platform. Actually, you have different solutions, but the goal is to reduce the number of clocks. So pop count is actually split in two different parts. The first one that aggregates the bits inside each 8-bit wide, and the second one that performs performs a tree, like a tree operation, a sequence of vector additions, and only at the end we have the arithmetic, the across vector arithmetic, the 8V instruction that is more expensive than the standard vector addition and produces one scalar result. So this here we have an input volume that is convolved and produces just one single output. So this is the case for one output channels. Now let's go about to see what are the frameworks available on the market, on the open source. So the most popular and the most complete framework is Lark, provided by Plumer AI, that it completely integrates within TensorFlow and TF Lite and gives a lot of support on that. And also there are a lot of highly optimized binary implementation. And then there is the BNN. This is another framework, but is more custom and less general than Lark, that relies on TensorFlow. So we primarily addressed as a target platform the Raspberry Pi 3B, where we compared basically for different input sizes and channels the read inference time of LCE and the BNN, and we basically compared on the same input image sizes and channels. So it starts on the left from the 3x3 convolution with an 8 and width of 56 by 56 by 64 channels, and then this kind of input images is taken directly from a VGG model. So after binary convolution at Betron, there is always max pool, so the image is halved at each one of these columns, and we arrive at the end on the right side of the graph. This doesn't seem to work anymore. Okay, where the image size is 7 by 7 by 512 channels. On the left part, you can see the effort only the binary convolution, while on the right side we took into consideration also the packing, the sign bit extraction, and the padding. And for the Raspberry Pi 3, our solution provides, in the best case scenario, 1.7 and 1.9 speed up compared to LCE and MBNN. And one of the differences related also to the sign bit extraction that we perform on the fly, having a more cache-friendly approach. We implemented everything with the Arminian intrinsics. So we didn't provide any custom implementation or in assembly for instance, for the Raspberry Pi 4, that is a more powerful architecture. And even in this kind of target, we can get comparable results. And sometimes we are better, sometimes we are equal, or a little bit more inference time. Now, I just want to show you the accuracy results. We compared on CIFAR-10 Street-Views number, taking in consideration VGG small and VGG 11 models. And we actually were not able to get the same accuracy as, for instance, the binarized neural network proposed, the seminal work on that. We got here for CIFAR-10 slightly less, but as anticipated before, we really do not care to get the same accuracy or better. We just want to find the best trade-off, but what really matters, it is the inference time. For VGG 11, instead, we were able to recover basically the same accuracy of the floating point model. Instead, for ImageNet, we didn't train from scratch the networks. We got the pre-trained models taken from the Lark Zoo on web, and it is the binary ResNet 18 and DesNet 18, and we just inserted the clipping operation in there, and we performed the second training step, fine-tuning the model, and in this case we recover the same accuracy. So just to sum up, I show you a way to train binary neural networks with a double training stage. This allows to get an improvement basically on the Raspberry Pi 3 architecture compared to the state-of-the-art frameworks. And the real goal with binary neural network is that it could be possible to really reduce a lot the amount of silicon area if they should be employed. So thank you, that's it.